You may have heard before that special relativity cannot deal with accelerating objects or accelerating frames, because special relativity only deals with inertial reference frames, and that we need general relativity to deal with acceleration. This is incorrect and is a common misunderstanding. In fact, special relativity can handle accelerating objects and accelerating reference frames just fine. I think now is a good time to explain the differences between special relativity and general relativity, so that we can understand where special relativity ends and where general relativity starts. Special relativity is a theory of relativity that we get when we take the speed of light in a vacuum c to be constant in all inertial reference frames. Special relativity ignores gravity, and special relativity only considers flat space-time. Meanwhile, general relativity is a theory of gravity that we get when we accept the equivalence principle, which says that a local gravitational field is completely equivalent to an accelerating frame. And so general relativity does take gravity into account. General relativity is a theory of curved spacetime and treats gravity as a manifestation of curved spacetime. Now, I realize that a lot of what I just said about the equivalence principle and curved spacetime probably doesn't make much sense right now. We'll be getting to those in future videos. But the point is that the main difference between special relativity and general relativity is that special relativity ignores gravity, whereas general relativity includes gravity. Special relativity cannot deal with gravity, but there's no rule that says special relativity can't deal with acceleration or non-inertial frames. That said, special relativity treats inertial frames and non-inertial frames as fundamentally separate situations. In inertial frames, the laws of physics, ignoring gravity, are all the same, and the speed of light is constant. When viewed from other inertial frames have constant velocity and have straight-line coordinate systems. Meanwhile, non-inertial frames experience extra fictitious forces in addition to the normal laws of physics. These fictitious forces depend on the reference frame, similar to when you get thrown into the back of a car seat when the driver steps on the gas pedal. In non-inertial frames, the speed of light is not constant. Later in this video, we will look at a non-inertial frame where a light beam appears to be frozen in space with zero velocity. When viewed from inertial frames, non-inertial frames have a changing velocity, or acceleration, and have curvilinear coordinate systems. It's important to note that, even though non-inertial frames in special relativity have curved coordinate lines, the spacetime they describe is still flat, like the surface of a table or a flat computer screen. On the left, we have a straight-line coordinate system drawn on a flat surface. And on the right, we have a curvilinear coordinate system drawn on a flat surface. Both coordinate systems describe flat geometry. We won't see truly curved geometry until we get to general relativity. The Relativity 105 videos are all about acceleration in special relativity. In this video, we'll talk about hyperbolic motion, which is what constant acceleration looks like in special relativity. We'll also show how acceleration leads to the creation of a Rindler Horizon, which is similar to the event horizon of a black hole. In the next few videos, we'll talk about Rindler coordinates and Bell's spaceship paradox, basis vectors and the Jacobian in curvilinear coordinates, proper time along curves and the twin paradox, the covariant derivative, and finally geodesic curves, which are the curves that inertial frames travel along. Let's start by talking about constant acceleration in Newtonian physics. You probably know that an object traveling at constant acceleration in Newtonian physics traces out the curve of a parabola, as seen by falling objects on Earth in everyday life. If we draw a parabola on a spacetime diagram with time on the vertical axis, we immediately see a problem. Recall that a beam of light travels at a 45-degree angle on a spacetime diagram. We can see that, in this portion of the parabola, the object is traveling faster than the speed of light, which we know is impossible from Relativity 104 Part D. So we know that an object undergoing constant acceleration in special relativity cannot trace out a parabola curve, because that would mean the object would eventually travel faster than light. Instead, we'd expect an accelerating object in special relativity to trace out a curve more like this, something that goes faster and faster but never actually reaches the speed of light. This curve of constant acceleration in special relativity is called a hyperbola, where the time and space coordinates are given by hyperbolic sine and hyperbolic cosine of a hyperbolic angle. See Relativity 104 Part E if you want to review hyperbolic geometry. To prove that constant acceleration in special relativity gives us a hyperbolic curve, we're going to follow 3 steps. Number 1, we're going to prove that the 4 velocity and 4 acceleration vectors of an object are always orthogonal. Number 2, we're going to define exactly what we mean by constant acceleration in special relativity. And number 3, we're going to derive the equations of motion for the space-time world line of an object traveling with constant acceleration. The first step is to prove that an object's 4 velocity vector is always Minkowski orthogonal to its 4 acceleration vector. In other words, u dot a equals 0. Remember, the ordinary Euclidean version of orthogonal means that 2 vectors meet at a right angle. But the Minkowski version of orthogonal means that 2 vectors meet at equal angles with a beam of light in a space-time diagram. The proof is easy. We just take the derivative of u dot u and use product rule over the dot product. Since the order of the dot product inputs doesn't matter, this is just 2 of the same term added together. The derivative of 4 velocity with respect to proper time, du by d tau, is just the 4 acceleration vector a. Now, we know that u dot u is always c squared, which is constant, so its derivative is 0. And dividing both sides by 2, we see that u dot a equals 0 always. We can think of this as being like a law of physics in special relativity. It makes logical sense that a is always orthogonal to u. Since the Minkowski length of u is constant, acceleration cannot make it longer or shorter. Acceleration can only change its direction. This means that all acceleration must be orthogonal to u, because acceleration can never be parallel to it, because that would make u longer or shorter. So we've proven that u dot a equals 0 always. The next step is to define what we mean by constant acceleration. In normal Newtonian physics, we could just say that constant acceleration means that the components of the 3 acceleration vector, ax, ay, az, are constant. But because time and space are relative in special relativity, Newtonian acceleration is also relative, and we need a new way of defining constant acceleration. Instead, we're going to define what is called the proper acceleration. Recall, the proper time for a moving observer is the amount of time measured by a clock that the observer is carrying with them. Similarly, proper acceleration is the acceleration measured by an observer using an accelerometer that they are carrying with them. You're probably familiar with the feeling of getting thrown backward inside an accelerating car, or feeling heavier when an elevator accelerates upward. It turns out that it's possible to build an accelerometer, which is a mechanism that measures accelerations like this. Most modern smartphones have accelerometers inside of them, and you can download an accelerometer app to measure your proper acceleration in different directions. In this video, we're going to look at the case of constant proper acceleration, which refers to an accelerating observer that always measures a constant number on an accelerometer that they are carrying with them. Let's say that the physicist Wolfgang Rindler is traveling along a world line with constant proper acceleration in the positive x direction. Let's try to understand his acceleration from his own reference frame and also from the frame of Einstein, who is standing still in a stationary frame nearby. We know that a Lorentz transformation can always change coordinates from an inertial frame to any other inertial frame, which has a straight world line. But a Lorentz transformation cannot change coordinates from an inertial frame to a non-inertial frame, because non-inertial frames have curved world lines. However, we can always find a Lorentz transformation that brings us to an inertial frame for one specific point on a curved world line. For example, the inertial world line of this rocket is tangent to Rindler's world line at exactly this one event point. This means at this event point, both Rindler and the rocket have the same 4 position and the same 4 velocity. So for this one instant in time, the rocket and Rindler have the same inertial reference frame, given by a spacetime basis et tilde and ex tilde. And we can find a Lorentz transformation from Einstein's stationary frame to this momentary inertial frame at this exact event point. This other rocket's inertial world line is tangent to Rindler's world line at this point. So this would be their common inertial frame at this instant. And for this other inertial world line, this would be Rindler's common inertial frame at this instant. So a curved world line in spacetime is like a series of instantaneous inertial frames, where every event point along the curved world line has its own inertial spacetime basis, where the time basis vector is tangent to the world line curve and the position basis vector is orthogonal to it. An instantaneous inertial frame is also called a momentary inertial frame, or a momentarily co-moving reference frame, MCRF. So while we can't find a Lorentz transformation that works for Rindler's entire world line, we can find a Lorentz transformation that brings us to an instantaneous inertial frame at any given point along his curved world line. Also, by definition, the 4 velocity vector is also tangent to a curved world line at any given point, because it must match the direction of the world line of an inertial observer. And as we've shown, the 4 acceleration vector is always orthogonal to the 4 velocity. So this means that in an instantaneous inertial frame, the 4 velocity u is always parallel to the time basis vector, because they are both tangent to the curved world line. This means that the 4 velocity vector always has 0 space components from Rindler's point of view. This basically means that the observer in this frame thinks they are always stationary in space. And the 4 acceleration a is always orthogonal to the 4 velocity. So this means that in the instantaneous inertial frame, the 4 acceleration is always purely in a spatial direction, with a 0 time component. So when we say Rindler has constant proper acceleration, this means that the components of Rindler's 4 acceleration vector are always constant and point in the space direction only for his instantaneous inertial frame. But the nearby stationary observer Einstein will see Rindler's 4 acceleration vector have a different mix of time and space components depending on when Einstein measures it. If we assume Rindler's acceleration is only in the x direction, then he would calculate his 4 acceleration a to be alpha times ex tilde, where alpha is the size of his proper acceleration. This means that a dot a equals negative alpha squared, where the negative sign means that a is a space-like vector. Even if the stationary observer Einstein sees the components of Rindler's 4 acceleration vector to be constantly changing, he will still agree that a dot a equals negative alpha squared for Rindler's 4 acceleration vector, because the dot product of 4 vectors is invariant and agreed upon by all observers, regardless of the reference frame. So our condition for an object having constant proper acceleration alpha in their own frame is that their 4 acceleration vector dotted with itself gives the constant value of negative alpha squared. This is true assuming that the acceleration is only in the x direction. Finally, the last step is to derive the equation of a world line traveling with constant proper acceleration. We are going to analyze Rindler's accelerating motion from Einstein's stationary inertial frame, with basis ET and EX. We are going to assume that no motion occurs in the y or z directions, so we only need to worry about the x-axis and the time axis. Our goal is to measure the components of the four velocity vectors u and the four acceleration vectors a along Rindler's world line, measured in Einstein's spacetime basis. We already know that it's always true that the four velocity dotted with itself gives c squared. In Einstein's frame, Rindler's four velocity dotted with itself equals ut squared minus ux squared. We also showed that it is always true that u dot a equals 0. In Einstein's frame, this means that ut-at minus ux-ax equals 0. Finally, in the special case of constant proper acceleration, we have a dot a equals negative alpha squared, which is at squared minus ax squared. We'll start with the fact that u and a are orthogonal. ut-at equals ux-ax. Then we'll square both sides. Now, based on u.u equals c squared, we can replace ux squared with ut squared minus c squared. And based on a.a equals negative alpha squared, we can replace ax squared with at squared plus alpha squared. If we distribute this multiplication, we get four terms: ut squared at squared minus c squared at squared plus alpha squared ut squared minus c squared alpha squared. Ut squared at squared cancels on both sides, and we can factor out alpha squared from both of these terms. We can move this to the other side and then replace ut squared minus c squared with ux squared. Taking the square root of both sides, we finally get at equals alpha over c times ux. And if we follow this process again from the beginning, but substituting for the time components instead of the x components at the start, we get another similar equation, ax equals alpha over c times ut. Now, it is technically possible that we could get either a plus or a minus sign when we take the square root here, but we're choosing the positive x solution because we want the observer to be accelerating in the positive x direction instead of the negative x direction. Now, since we are observing from an inertial frame, basis vectors are constant everywhere in spacetime, and their derivatives go to 0. This means that we are lucky, and the derivatives of the components of the four velocity are exactly equal to the components of the four acceleration. So at equals dut by d tau, and ax equals dux by d tau. So we have two coupled differential equations. Alpha over c ux equals dut by d tau, and alpha over c ut equals dux by d tau. The first step is to multiply both sides of the second equation by c over alpha. This basically moves the constant from the left side of the equation to the right side and takes the reciprocal. Given this pair of differential equations, we can sub ut from one into the other, and then we get ux times alpha squared over c squared equals the second derivative of ux with respect to tau. If you know about differential equations, you might know that there are exactly two kinds of solutions to the problem of a function being proportional to its second derivative. The solutions are e to the alpha over c times tau, or e to the negative alpha over c times tau. You can plug either of these solutions into ux in this differential equation to confirm that they work. In fact, any combination of these solutions added together with constants k1 and k2 also works, and you can plug this into ux to confirm that this is true. Now, differential equations always have multiple possible curves as their solutions, depending on the constants that you choose. In order to get unique constants, we need to choose an initial condition. Let's say that our initial condition is that the x velocity is equal to 0 when tau equals 0. So the 4 velocity vector only points in the time direction at time tau equals 0. So if we take ux and set it to 0 when tau equals 0, we get that k2 equals the negative of k1. And subbing this in, we can factor out k1 from our formula for ux. We can then plug ux into this second differential equation that we had, and we get a formula for ut. And when we take the derivative, we get an extra factor of alpha over c in front, which cancels with c over alpha. Also, the second exponential changes sign because we took the derivative of a negative exponential, so the minus sign comes out in front. So the formulas for ux and ut are the exact same, except for the sign of the second exponential term. Now, we know that ut and ux are not independent of each other, because we know that u.u equals c squared for any 4 velocity vector. This law should apply for all values of tau, so let's plug in tau equals 0 to simplify the formula. We know that when tau equals 0, we said that ux equals 0, because of the initial condition that we chose. And plugging tau equals 0 into the formula for ut, the exponentials to the power 0 just go to 1 plus 1. Taking the square root of both sides and dividing both sides by 2, we get that k1 equals 1/2 c, half the speed of light. We're taking the positive solution to the square root to ensure that our 4 velocity vectors point from the past to the future instead of the future to the past. Now, it turns out that for some variable phi, 1/2 times e to the phi plus e to the negative phi is equal to hyperbolic cosine of phi. And 1/2 times e to the phi minus e to the negative phi is equal to hyperbolic sine of phi. You can pause the video and prove to yourself that the fundamental identity cosh phi squared minus sinh phi squared equals 1 is also true for these exponential formulas. So really, these are just two different representations of cosh and sinh. So really, ut is just c times cosh of alpha over c times tau, and ux is just c times sinh of alpha over c times tau. It's also easy to see that the derivative of cosh phi with respect to phi using the exponential representation is just sinh phi. And the derivative of sinh phi with respect to phi is just cosh phi. Given these formulas for the 4 velocity components, it's easy to check that u.u equals c squared, as expected. Using the time and x components for the 4 velocity, we can immediately get the components of the 4 acceleration by taking their derivative with respect to tau. And we can see that a.a equals negative alpha squared as expected. We can also get the space-time 4-position components by taking the integrals of the 4 velocity components with respect to tau. And we get integration constants kt and kx added on at the end. These integration constants represent another initial condition, the initial position in space-time of the accelerating observer. For simplicity, we'll set them to 0. This means that our initial time position is 0, and our initial space position is c squared over alpha. We can also see that, in this special case, the observer has a constant space-time interval, s.s, of negative the square of c squared over alpha. The proper time tau is the time that Rindler measures on his own wristwatch as he travels along his world line from bottom to top. With negative tau being on the bottom half, tau equals 0 is the point where he crosses the x-axis, and tau greater than 0 is the upper half of the world line. If we draw the initial conditions as vectors, the 4-position s at tau equals 0 is c squared over alpha on the x-axis, and the initial 4 velocity at tau equals 0 is parallel to the time axis with magnitude c. This is because we said that the 4 velocity initially had 0 x component. So we've confirmed that a world line of an object undergoing constant proper acceleration is indeed a hyperbola, parameterized by hyperbolic sine and hyperbolic cosine, with the alpha parameter indicating how strong the observer's constant proper acceleration is. The last thing I want to talk about is an interesting phenomenon related to acceleration in special relativity called the Rindler Horizon. The Rindler Horizon phenomenon is named after the physicist Wolfgang Rindler. Let's say that Einstein is stationary and Rindler is undergoing constant acceleration on a hyperbolic world line. And let's say that Einstein sends beams of light toward Rindler at constant intervals in time. We see that the first few light beams reach Rindler with no problem, but after a certain point, the light beams will never catch up with Rindler. Because Rindler is going faster and faster, he is actually able to outrun beams of light when they are sent from far enough behind him. Basically, any beams of light that are sent from this shaded region of space-time will never reach Rindler. This means that there is a boundary behind Rindler where everything behind the boundary appears as complete darkness to him, because light from behind the boundary will never reach him. This boundary is called the Rindler Horizon. Nothing from behind the Rindler Horizon, not even light, can ever reach or influence Rindler. In some ways, this is similar to the horizon of a black hole, where nothing behind the horizon of a black hole can ever get outside of it. In this case, nothing that is sent from behind the horizon can ever cross through to the accelerated observer's side of the horizon. However, unlike black holes, the Rindler horizon is ultimately artificial. As soon as Rindler stops accelerating, the light beams will catch up with him again. Black holes, on the other hand, are actually physical and can't be removed by changing reference frames. An interesting question to ask is, how far behind Rindler is the Rindler horizon? We can figure this out by looking at the various position basis vectors along Rindler's world line and measuring the distance to the Rindler horizon, parallel to these position vectors. Since all of these position vectors meet at the origin, this is the same thing as just measuring the length of Rindler's various 4-position s vectors. If you recall, for our hyperbolic world line, the space-time interval s.s is a constant number for all time, negative the square of c squared over alpha. This means that when Rindler looks back, parallel to his x-position basis vector, he will observe a proper distance L0, which is the square root of minus s.s. This means that Rindler sees a horizon, specifically the origin, to be a constant distance of c squared over alpha for all time. So what is normally a distance that gets larger and larger from the point of view of Einstein's stationary frame becomes a constant distance in Rindler's frame because of the increasing effect of length contraction. So the Rindler horizon is always a constant distance behind Rindler, even though he is always moving forward. This means that a beam of light released on the Rindler horizon, for example, a beam of light released at the origin of our space-time diagram, is always a constant distance behind Rindler. The speed of the light beam, according to Rindler, is actually 0. So the postulates of special relativity say that the speed of light in a vacuum is always c equals 300 million meters per second in all inertial reference frames. But in non-inertial reference frames, the speed of light can have different values, even 0 in some cases, as we've seen. It also turns out that Rindler will never see any objects fall behind his Rindler horizon. Anything that gets close to the horizon will experience so much time dilation from Rindler's perspective that it will almost freeze in place. It will very slowly approach the horizon, but it will never cross it from his perspective. Remember, time dilation means that moving clocks run slow. So from Rindler's perspective, any objects that approach the Rindler horizon will have such significant time dilation that they will almost freeze in place. The object will very slowly approach the horizon but never cross it from Rindler's perspective. So to summarize this video, we found that a curved world line is a series of instantaneously inertial reference frames, where every point on the world line has a different inertial frame, where the time basis vector is tangent to the world line, and the position basis vectors are Minkowski orthogonal to it. We also learned that for velocity and for acceleration are always Minkowski orthogonal to each other, with a dot product of 0. We learned that proper acceleration is the acceleration measured on an accelerometer carried by an observer. And we learned that the condition for constant proper acceleration alpha is a dot a equals negative alpha squared. This assumes that acceleration is only in the x direction. And we also learned that objects traveling with constant proper acceleration have a hyperbolic world line according to inertial observers. We also learned that accelerated reference frames can actually outrun beams of light, and there is a constant distance behind accelerating observers called the Rindler Horizon. And the distance of the Rindler Horizon behind the observer only depends on the value of the acceleration, alpha, and the speed of light. Light beams sent from behind this horizon can never reach or influence the accelerated observer. And light beams that are sent exactly on the horizon will appear to be frozen in space from the perspective of the accelerated observer.